Hello, here we'll be solving problem 8.2. This is book problem 13.24. And what they give us is two masses and two spring constants in this diagram. And they ask us to find the spring modes and interpret it. So, as I did here, I drew our free body diagram, the direction of x of that mass 1, the direction mass 2, and then just kind of piece together the direction of force accordingly. And with that, as you probably remember, we'll get these equations, and from there we can combine them to build our equation of motion. And as I did, you can see for the first mass, just kind of rearranging the terms, we'll eventually get to this. And here I moved all the x1 terms together, which are just both the k's, and separated the x2. And likewise for the second mass, as we have an x1 and an x2, I separated those here all on the left-hand side of the equation, which will help us here in a second to put this into the right form. So after we have our two equation of motion, we can then sort of make a matrice out of this, and then further examine this problem to figure out the solution for the modes. And so as I've done here, you can see by using the properties of matrices that this will build this equation if you perform the right I guess algebra, matrix algebra to it. And as I've kind of outlined here, that this is what it basically gave us in kind of a shorthand way. And as we get this mapped out, we can then solve for our x, so to speak. And as we do that, we'll use the trial solution method. And as you can see here, with this expression, we'll assume this. And the two things that we'll have to consider is that this determinant will equal 0, and this term, the x is a trial solution that is also equal to 0. And so as we apply this to our two matrices here and add them together, you can see we can build our mathematical expression this way. And then when we find the determinant of this, it's basically multiplying these two, and subtracting, as you can see I did right here. We gain that expression that way. And then as we take our terms that we were initially given, the m1 and 2, k1 and 2, and plug them into that equation, we are able to solve for the s squared that was brought into this expression here to help us solve for that s. And as you just crunch some numbers, you will have to use the quadratic formula. And you get two numbers, and just approximating to the next highest number, you we'll get the negative 192, negative 3475. And of course, those are squared, so you take the square root, you get, well, it's a negative number, so you get the imaginary, you get the j. And so there's actually 4 solutions, 2 of each. Well, now that we have that s, or rather the s squared, and all this given information, we can now solve for that, for our initial x. And so as we plug it back into the equation that we defined up here with the numbers, you can see that we get this layout, and multiplying through the 192 to here, and then adding the V1 and the V2. Now, you'll have to remember when adding matrices, you do it by the component. And so what was interesting, I thought, is that you get actually a slightly different number on each top, like on each row. But for the first 4 numbers, they're exactly the same. So I'm not sure why that is, but I think it's safe to say that that's going to be 1, V2 is going to equal the 1.404. And with that being the positive value, that's your in phase mode. And when you apply the same rule to, I guess when you apply that same equation to this S, follow the same mathematical expression, you still get a similar discrepancy, or I guess difference rather, in the number, but it's for the first 3 numbers, almost 4 is the same, and this is a negative value here. So if that was a 1, V2 would equal the negative 0.2375, and that is actually out of phase, which I didn't write on here, but those are your modes. And hopefully this helped you. Thank you for watching.